Let's continue our 6.4 Day 2 notes with the final two graphing examples. Y equals -2 cosine pi over 3x. Notice in this example we have an A value and a B value. If A equals -2, that means the amplitude is the absolute value, which is 2. And 2 is greater than 1. That means this graph is going to stretch vertically. Also note, because A was originally negative, it's going to reflect over the x-axis. The B value has pi in it, and we talked about this from the first video. If B is pi over 3, we automatically know we're going to have to approximate our graph. And you'll see on the graph that I've given you that there's no pi values. It's just our integer values for x. Because B is pi over 3 is slightly greater than 1. And that means our graph is going to compress horizontally. All right, so let's see how we get that. The first thing we're going to do is just set bx equal to 0. And again, for this lesson, everybody, pi over 3 times x equals 0. No matter what we multiply on that right-hand side, we're just going to get x equals 0 to start with. So this is great for us for now, just to kind of get the practice of changing these values. To set bx equal to 2 pi, however, now if we have pi over 3x equals 2 pi, and I multiply by 3 over pi here. Oh, if I can get that to fit in there, sorry. The pi's cancel and the 3's cancel. Pi's cancel on the right, and 2 times 3 is 6. So you'll notice we'll start at 0 and end at 6. Now normally we end at 2 pi, which is 6.3, so this really isn't that much of a compression for the function. Speaking of functions, let's start by graphing the parent function cosine. Y equals cosine x. And what I'm going to do, you guys, is I'm going to extend my x values using all of those decimal approximations so that we can plot them on our coordinate system. All right, all of a sudden a lot is on your screen right now. I get that. So I took my x values, and these are the values that would be the translation, or that would be the original parent function. So I did 1.6, 3.1, 4.7, 6.3. And then I just continued the rest of those numbers from the other page, just to kind of give you quick reference to kind of approximate where cosine is on this graph. I know it's a little tricky to get these on here. And then I just went 1, 0, -1, 0, 1, and continued the pattern. 0, -1, 0, 1, 0, -1. And I went in the other direction as well. So pause the video and plot these points accurately as best you can on your graph, and then press play and we'll finish this transformation. To get the transformation for y equals -2 cosine pi over 3x, we note that for the x values, we start at 0, and then we need to go our 1, 2, 3, 4, and we have to end at 6. And that would be the 1 period for that function. So then halfway between 0 and 6 is 3, so that's easy to fill out. Halfway between 0 and 3 is 1.5, or 1.5. Okay, so at least we know that that's going to be consistent, 1.5. And then between 3 and 6, half of that is 4.5. So those are going to be our new input values. And notice they're not much smaller than those first 5 ordered pairs from the parent function. So this is a very slight compression. All right, for the y values, I noticed that we have to multiply everything by -2. So 1 times -2 is -2. 0 times anything, 0. -1 times -2 becomes positive. Back to 0, and then 1 would be multiplied by -2 to get -2. If we plot these values, 0, -2, 1.5, 0, it almost overlaps with the other one right at the same spot. 3 up to positive 2, and then 4.5 back to 0. So now you can kind of start to see it's a little bit to the left, a little bit compressed, and then it's 6 down to negative 2. If we continue this pattern, see if you can follow along. If I go 1.5 more, I'm at 7.5, and then I'm back to 0. 1.5 more is 9, and I'm up to positive 2. 1.5, 10.5 down to 0. And then 1.5, 12 down to negative 2. 13.5 back to 0. 14.5, 15 up to 2. And that's to the right-hand side. So if I go back to 0 and I go 1.5 to the left, I'm at 0. If I go to negative 3, I'm up to 2. 1.5 more, negative 4.5, back to 0. 1.5 more, negative 6, I'm down to negative 2. So those dots look like they're pretty consistent in this pattern. Let's see if we can create this curve. I'm going to start all the way over here at the right to see if I can find all my dots. Come down, back up, and down again. Just trying to draw a nice smooth curve through all of those orange ordered pair values. Arrow on the left, I'll come back over here, arrow on the right. So there's our transformation, which is a stretch vertically, a reflection over the x-axis, and a compression horizontally. All right, let's try one more. Y equals 3 sine 2x. Oh, goodness, no more pi for the b value. So notice all of our ordered pairs at the bottom are exact. Good, for now. All right, a equals 3. With that, we know that the amplitude would then just be the absolute value of 3, which is 3. And since 3 is greater than 1, this graph will stretch vertically. There we go. B is 2. Because of that, we know 2 is definitely greater than 1, and that means the graph compresses horizontally again. This time, let's determine our new start and end value without having pi in b. If we set bx equal to 0, that would just be 2x equals 0, divide by 2, and again we start at 0. There's our new start, which is the same as the parent function. But when we end this time, if we set it equal to 2 pi, and if 2x equals 2 pi, now if we divide by 2, the graph will end at 1 pi. So that's definitely a compression that we'll see when we have both of the graphs on our system over on the right. All right, so let's start with the parent function. We know this is the sine wave. So when we make our table, we're using our exact values from the parent function. 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then remember, sine at 0 starts at 0, so it goes 0, 1, 0, negative 1, and 0. I'm going to let you pause the video again and graph this on the coordinate system from edge to edge. Then press play, and we'll finish this final graph. All right, here is our parent function for y equals sine x. Let's take a look at what's going to happen with our new function, y equals 3 sine 2x. This is going to get a little interesting, everybody. When we make our new input values, I know we're going to start at 0, and then we have to go 1, 2, 3, 4, and end at pi. So we've got half the amount of time to finish this sketch. All right, so between 0 and pi, halfway is pi over 2. But if we go between 0 and pi over 2, halfway between that would be pi over 4. We haven't graphed pi over 4 yet, and it's not even marked on our charts. We're going to have to, on our table. We're going to have to figure out where to put that on the x-axis. And then between pi over 2 and pi, halfway between that would be 3 pi over 4. So let's see how to make this happen on our graph. Do you see right here we've got 0 and pi over 2? Halfway between, we're going to have to make a dash right there. We're going to have to create our own location for that pi over 4 and 3 pi over 4. So notice between each of the dash marks that are already on there, right in the middle is where we're going to have to be. So I'm going to kind of plot all those in here really quick. That's where all of those denominators of 4 will be, like the 1/4 and the 3 pi over 4, that kind of location. We have to get those all the way in here because we're going to plot something at every one of those locations. This is going to be great. There we go. And then on the other side, we get to do the same thing right in the middle, middle there, and then right on the edge over there at the left. Those are our inputs, all right? For our outputs, because A is 3, we're going to triple all the y values. So if I multiply 0 by 3, that stays 0. 1 by 3 is going to be 3. Then we go back to 0. -1 times 3 drops down all the way to -3. And then we at least end at 0. Let's see. So if I go up to 2 and 3, I'm right at the very top. 2 and 3, -3 at the bottom. All right, watch how compressed this graph is. All right, I'm going to even zoom it out a little bit. Let me see if I can do that for you. I don't know, last time this didn't want to do that much for me, so let's see. There we go. I want a nice big graph so it's easy to see what's happening here. Okay, so if we go 0, 0, we'll stay right here at the center. And then pi over 4 is that purple dash that's like 1.5 kind of on the graph itself to the right. That means that's going to put us up to +3 up here kind of in the middle. And then at pi over 2, we're back down to 0. 3 pi over 4 is that next purple dash. Notice we're down to -3. And at pi, we're back to 0. So that's one full loop for the period of the function with that b value of 2. And now we have to continue this pattern. So after pi, that next purple mark, I'm going to go up to 3. And then at 3 pi over 2, back to 0. Purple dash mark down to -3. 2 pi, back to 0. Up, back to 0. All the way down, back to 0. Up to that 3, and then kind of continue that pattern all the way till we get to the, oops, that one's off. Hang on. That one's not supposed to be on an actual grid mark. It's in the middle. There we go, kind of. And then back to 0. I'm just talking to myself. It's great. Here we go. Down here and up to the top. Whoa, all right, I'm just going to sketch that much of it for now and see where we're at. Watch what happens with this graph. It's going to curve way, way up and then come right back down, go way up and then come right back down. Whoops, missed it a little. Go back up again, down. A little off with my pen, sorry. There we go. I'm trying to get this to come back down and up and down. And up again. There's that side. And then over on the left, we get down to -3 on the purple mark, back up to 0, up to 3, back to 0, and so on. And as far as I'm going to go. Drop this down, curve it back up and down and up and down like so. And there is that compressed horizontally and stretched vertically graph y equals 3 sine 2x. There's the final example in your 6.4 day 2 notes.